Math 31. We are now looking at slant asymptotes, sometimes called oblique asymptotes. So asymptotes that are neither horizontal nor vertical. So an asymptote is always linear. So even though it may turn out that as a function approaches infinity, it may approach a parabolic shape, we don't call that an asymptote. So we only have asymptotes if our graph approaches a line as x approaches positive infinity or negative infinity. So here on this first page of our notes for section 5.6, I've asked you to use limits to determine the equation of horizontal asymptotes if there are any. So we have 4 questions here. The next page is also warm up, but I'd like you to do these 4, then restart the video, and then go on to the next 4 after we review these. So you can pause the video at this point, restart once you've finished these 4 questions. All right, for this first question, remember to find limits for horizontal asymptotes. We're doing the limit as x approaches positive or negative infinity. And one strategy was to look at the highest degree x in the denominator, multiply numerator and denominator by 1 over that power of x. Then we can see that in our next line, this 2 over x goes to 0, this 1 over x goes to 0, and I'm left with 0 over 1, which is 0. So I have y equals 0 as a horizontal asymptote. Number 2, similar process. I have an x plus 1 in the denominator, multiplying. I have these factors that go to 0. That would be this one and that one go to 0, which leaves me with 2 over 1, and y equals 2 is the horizontal asymptote. Question number 3. As x approaches infinity, now in the numerator, as I look at what cancels out, this 3 over x and that 3 over x, those are both going to 0, but I still have an x in the numerator, and so that reduces to 2x plus 3. As x approaches positive infinity, this will approach positive infinity, the whole function, and as x approaches negative infinity, this whole function will approach negative infinity. So really, I should look at these two limits separately if I'm interested in what's happening to the graph. In this case, I'm only interested in horizontal asymptotes. There are none. Question number 4. We will see a similar thing happen this time. Once we simplify things down, we have a quadratic. And as x approaches positive or negative infinity, this squared term will dominate. So our function will approach positive infinity, no horizontal asymptotes. Okay, so now in these next questions, we're going to do something a little bit different. I want you to divide to rewrite each function in the form some quotient plus a remainder over the divisor. So a little bit similar to what we did in Math 30-1, only this isn't the typical form that we wrote it in. So let me just demonstrate with question number 5 here. I'm dividing x plus 1 into 2. How many times does it go in? 0. So I have 0 plus 2 over x plus 1. Well, a little bit silly. In other words, I can't divide this. I can't simplify it or reduce it any further. Okay, but it's in the form quotient of 0 plus my remainder of 2 over my divisor. Maybe I'll do question 6 with you and then give you some time for 7 and 8. Dividing x plus 1 into 2x plus 3. Well, x goes into 2x twice, so there's my quotient. I've written my quotient down here. 2 times x plus 1 is 2x plus 2. When I subtract, I get 1. That's my remainder. That goes in the numerator over the divisor. So it's kind of like mixed numbers. So this is like 2 and 1 x plus 1th. All right, pause the video at this point. And why don't you do questions 7 and 8, do that division, and rewrite it as quotient plus remainder over divisor. You can pause the video now, restart once you've finished these two questions. Question number 7, here's what I have. You can look over the process. Here is my quotient from above there. My remainder was 2, so I have 2 over x plus 1 added on at the end. Question number 8, similar process. And once again, we're getting a remainder of 2. That won't always happen. These questions are just set up as kind of similar functions. But again, I have my quotient is this quadratic plus divisor over remainder. Well, all of this is setting the stage for finding slant or oblique asymptotes. So here, just to help us focus, let me put this screen in place. So a slant asymptote, suppose some function y equals f of x has a non-vertical asymptote line and also not horizontal. Then the following must be true. Actually, non-vertical. This will give us horizontal or vertical asymptotes. No, let me restate that. It will give me horizontal or oblique asymptotes, not vertical asymptotes, this process. So what we're going to discover is as x approaches positive or negative infinity, our function will approach a line. That makes sense? That's what an asymptote does. So I'm going to state the same thing in a different way. The difference between the function and the line will approach 0. So if the function is getting closer and closer to the line, then the distance between the two of them goes to 0. Makes sense. So using limit notation, and notice here this is x approaching infinity. Double check that your notes are correct. You may have an n there by mistake. As x approaches positive or negative infinity, the difference between the function and the line, this subtraction, that difference will go to 0. Or f of x minus some line mx plus b, that difference will go to 0. If this is true, then our function has a non-vertical asymptote. Doesn't mean it doesn't have a vertical asymptote. It just means it has a horizontal asymptote or an oblique slant asymptote. Okay, we're going to make use of this as we go through these next examples. But just a note here that even though this is really important and a clear description of the conditions for an asymptote to exist, what we're going to discover is using this limit process becomes pretty tedious and seems unnecessary fairly quickly. But we are going to keep using it for the next 4 questions, and then we'll look at shortcuts after that. Okay, so question number 9. We want to use limits, and so here's the limit that we're going to use to determine if each function has a non-vertical asymptote, and we'll determine the equation of that non-vertical asymptote. So here's the h of x function. This is the same function as we looked at in question number 7. So I've already done division, and that's the first step we need to take. I need to rewrite this as some polynomial plus a simplified rational expression where my numerator is lower degree than denominator. That's what happens if I get a remainder over the divisor. So the limit as this thing goes to infinity, well, this part will go to 0. I'll be left with a line. Well, there you go. We already know we're going to have an oblique asymptote. But here's the process using these limits. I will take the limit as x approaches infinity, and I'm just going to do positive. I won't do positive and negative here, of my function. So here's my function after I've done long division. So keep in mind, long division is part of this process. It's just that we did it earlier in question 7. And I'm going to subtract the line. So I'm doing the difference between the function and a line. How did I decide on this linear expression here? Well, I just looked at my function and saw I had a linear expression there. That's what I want to subtract out. When it gets subtracted out, I have just this rational part. And as x goes to infinity, this rational part goes to 0. That was the condition up here. The distance between the function and the line is going to 0. Here's my function. Here's my line. Subtract to get the distance between them or difference between them. That difference goes to 0. Therefore, y equals 2x plus 1 is an asymptote to the function y equals h of x. Next question. This is the question that we looked in number 8. I don't know if I changed that number. Nope, still says number 7. Well, let's change that to question number 8. In question number 8, we did long division to this function to rewrite it in this form. Well, we can already see, I can see, hopefully many of you can see that this is not linear, so this is not going to have an asymptote. So here's how we use limits to show that. Here I have my function, subtract a line. How did I decide on this line? Well, I just picked the linear part of this expression, the x plus 2. And if I subtract that out from my limit as x approaches infinity, I get 2x squared plus the rational expression. Well, if I do the limit of a sum, I can do the sum of limits. So as x approaches infinity of 2x squared, well, this is going to be infinite. And as x approaches infinity of 2 over x plus 1, that's going to 0. So infinity plus 0 is not 0. Therefore, this function, k of x, does not have an oblique or a slant asymptote. So the next two questions are check your understanding. I'd like you to go through the same process to show that there is a non-vertical asymptote to each of these. So at this point, please pause the video and you can restart as soon as you've finished questions 11 and 12. They may be misnumbered in your notes, but this is how they're numbered in my notes. In case you forgot, we need to do a long division first. So here's a long division, and this is not an easy long division because I end up with a fraction in my quotient. So let's just walk through this division process together. So I started by saying 3x. How many times does it go into negative 3x squared? Well, that's a good question. Let's try this once more. That first pullout had a mistake in it, as many of you recognized right away. We do need to do long division first. But here's what we get. And we are getting relatively nice numbers, so I won't go through the details of this process. Number 12 has more of a challenge in it, so we'll take some time on that one. So I'm getting a quotient of negative x plus 2, linear. That's good. I'm expecting an oblique asymptote, and I have a remainder of 5. So my function I can rewrite as that linear expression plus 5 over 3x minus 2. So here's what we do with the limits. The limit of our function minus that line, negative x plus 2, and we're doing the limit as x approaches infinity. Well, the linear parts cancel out, which is spectacular, which means we're looking at the limit as x approaches infinity of this rational expression, numerator is a lower degree than the denominator. This goes to 0. Perfect. That means y equals negative x plus 2 is an asymptote, an oblique asymptote, for the function y equals f of x. Now let's look at number 12. Number 12 has an added challenge. Because my divisor has this 2 coefficient in front of the x squared, whereas my numerator, my dividend, just has a 1 in the coefficient. So I end up getting some fractions as I do this division. There we go. So remember I have that missing term, 0x's, so I need to make sure I put that in as a placeholder. In Math 30-1, we only divided by linear functions in the denominator, so where we just had x to the exponent 1, but we can do long division with higher degree polynomials too. But remember, we need that placeholder. So 2x squared times what gives me x cubed times 1/2 x. So that's the challenge to begin with. When I do a half x times 2x squared, I get x cubed. Perfect. When I subtract, these will cancel. That's what I want to see. A half x times 0x is 0x squareds, which is 0. And a half x times -4 gives me -2x. We'll subtract, and then the process is similar to what we've done in the past. So what I'm ending up with here is my quotient, once again, a linear expression. So I am anticipating getting an oblique asymptote. Here's my function, rewritten in this form. Again, my numerator is lower degree than the denominator, which results in, when I take this limit, subtracting that line, 1/2 x minus 4, I will get this whole rational expression simplifies down and gives me 0 for my limit. So since my limit is 0, I can conclude what I have in red here is an asymptote for my function. So y equals 1/2 x minus 4 is an asymptote to the function g of x. So as you can see, really all we need to do is this long division part here. And if in this long division part I get a linear quotient, that tells me I'll have an oblique asymptote. When will I get a linear quotient? If my numerator is 1 degree more than my denominator. This process also works for horizontal asymptotes. We didn't do any examples like that, but you could test it out and see. So here's a shortcut that we will take. If some function is equal to a polynomial divided by a polynomial, rational expression, and I can rewrite that as a linear function plus remainder over divisor, then that linear function that we got here is going to be an asymptote to the function. So we will not always be doing these limits, but the limit is how we define the asymptote. There we go. Thus ends chapter 5.